So in this chapter, we're going to talk about dipole moment and resonance. They're not related to each other in any way, but this is all still your fundamentals, and we have to learn about these two. You learn both of these things in General Chemistry 1 and 2, so you can open up your old notes if you want. Dipole moment indicates whether a molecule is polar or not. Dipole moment, which is mu, Greek letter mu, is when a molecule can move in the presence of an electric current. The higher the polarity of the molecule, the higher the dipole moment. Dipole moment is actually a number which is measured quantity, so it's not just a random thing, it's actually a measured number that's given. So the higher that number is, the higher the dipole moment is. Ionic compounds are going to be inherently polar because of the presence of ions. The ions are cations and anions, and so because of those two, it's polar automatically, and so it has a really high dipole moment. Diatomic molecules that have the same atoms, like hydrogen, chlorine, iodine, these are also called homotopic molecules. These are going to be nonpolar because there is no difference in electronegativity. In this chapter, or for dipole moment, you really have to know electronegativity well, which we've done in chapter 1 already. So you should know what the trends are for electronegativity. And you will also have to kind of remember some of the differences in the bond. So for example, when you have a polar covalent bond, that polar covalent bond is because the electronegativity difference between the two atoms is more than 0.5. If it's less than 0.5, then it is a nonpolar bond. So for example, CH bond, CI bond, those are nonpolar bonds. Okay, so those are some things that you have to remember. Again, I wouldn't say, do all the calculations all the time, but know the trend. So any molecule that has a polar covalent bond can have a dipole moment, and that depends on the shape. And so the shape is important in the sense it means if you have a symmetric shape or an asymmetric shape, all right, that's when it can have a dipole moment. And of course, it's also dependent on the electronegativity or the polar covalent bond, which again we did in chapter 1. So make sure you review that. So how do you determine the dipole moment of any molecule? Well, these are the steps that you take, and if you follow them straightforward, then you should not have any issues at all. So first of all, write the Lewis structure. Write the correct Lewis structure of any molecule, which means write all the lone pair of electrons, and especially on the central atom, because that will help you to determine the shape of the molecule, which is the second step, and that is determine the shape of the molecule. Shape of the molecules, of course, is bent, trigonal planar, trigonal pyramidal, tetrahedral. Those are the 4 shapes, and linear. Those are the 4 or 5 shapes that we deal with in organic chemistry. The third thing is to identify the polar covalent bonds in the molecule. That is where you need the periodic table, and you need to know the difference in the electronegativity. You don't have to know the numbers. A general trend is good enough. And in some cases, if you do a few examples, which means if you do a few subtractions, then you can kind of keep in mind about which bonds are polar and which are not so polar covalent. So for example, the Ci bond is not that polar, however, the CCl bond is quite polar, okay, in its nature, which means that the difference in the electronegativity is a lot more for CCl bond than for the Ci bond. So if you do a few of these calculations in advance, you will have something in mind at least, okay, of what's a polar bond and what's not. Then, of course, you see if there is an asymmetric pull in the molecule, which means is there asymmetry in the molecule or symmetry in the molecule. So this is the last step that you do for dipole moment, and this is one of the most important steps also, which you can do only if you have the shape right. And again, you can get the shape right only if you have the Lewis structure correct. So all of these steps are important steps. The 3 molecules here, water, methanol, ammonia, these all have very high dipole moment, so mu. And then this is D, capital D is Debye, and that is the unit for dipole moment. So for water, there is a dipole moment. Dipole moment is indicated by this arrow with a little cross here on it. And the arrow points towards the negative charge, where oxygen is more electronegative than hydrogen. So oxygen has the delta negative and hydrogen has the delta positive. So the arrow is pointing more towards the negative side. Here, this is methanol. And in case of methanol, oxygen is more electronegative than carbon. And because of the shape of the molecule, which is bent, there is an asymmetric pull towards oxygen. Okay, and that's where the arrow is pointing then. In case of ammonia, nitrogen is very electronegative. And so there's an asymmetric pull towards nitrogen, and that's where the arrow is pointing then. Please remember, this arrow that is pointing has a crosshair on it, and this is the only arrow that we use for dipole moment. Here are some examples of dipole moment of some molecules. So you can see here sodium chloride 9. That's really very high. Okay, and that's because it's an ionic compound. So as I said, inherently that's going to be of a very high dipole moment. Okay, and then CH2O, if you don't know the Lewis structure of this, you should draw it out. Of course, the highly electronegative elements like oxygen, nitrogen, and fluorine will all show very high dipole moments unless there is symmetry in the molecule. But otherwise, most of them will have really high dipole moments. So by the time we come to these molecules here, they have very low dipole moment or zero dipole moment. So carbon dioxide, methane, and then ethane, benzene, no dipole moment. So these are the structures of the molecules that have no dipole moment, and you can see that they are symmetrical in nature, okay, which means carbon dioxide, which is carbon in the middle and oxygen on either side, is a linear structure. And even though carbon and oxygen is a polar covalent bond, but because the pull is equal on both sides of carbon and because of its linear shape, the dipole moment is zero. So it's almost like a tug of war. That's how I see dipole moment. So if the atoms are pulling equally on either side, then they nullify each other. Same thing happens with methane. The other thing about methane is that the carbon-hydrogen bond is not that polar to begin with. However, in this case, it's a symmetrical molecule too. Same here goes with ethane and then benzene. All of these are symmetrical molecules, and in some cases, like carbon dioxide, the dipole moment will kind of nullify each other because, or the polar covalent will nullify each other because of the symmetry in the molecule. So there is no dipole moment in these cases. So what is the purpose of the dipole moment? Why do we need to know it? In any case, in fact, in all cases, not just organic, it's really helpful in determining the physical property of the molecule. So it's really important you know the dipole moment. It's not important to know the exact number. It is important to know which molecule will have a dipole moment and which one will not, which one will have low or high. So as a comparison, one should know, okay, what the dipole moment is, not the actual number of it. So in any case, what are the physical properties that we will be talking about in organic for dipole moment? One of them is solubility. And so polar molecules will dissolve in polar substances. Okay, so like dissolves like, that's how the rule goes. So that's why you need to know the dipole moment here. Boiling points and melting points. The higher the dipole moment, the higher the boiling point and melting point of substances. So for example, sodium chloride is really high melting point because it is polar, has a high dielectric constant or dipole moment. Whereas naphthalene or benzene, they have very low boiling points because they have no dipole moment. And carbon dioxide, if you know, of course, it's a gas, okay, because it has no dipole moment. Vaporization, and so this is dependent on boiling point, and I kind of put it separately because almost all organic compounds are volatile. Volatile meaning that they give off vapor all the time, and the reason they give off vapor all the time is because they have low dipole moment, okay, in them, and that affects their intermolecular forces, which we're going to talk about. So if the intermolecular force is low, and that is because the dipole moment is low, then compounds will start vaporizing, okay, because they have low boiling points. There is no attraction between molecules. So vaporization is a really important thing for us because a lot of organic compounds are flammable, and if they're vaporizing, it means that you have a lot of flammable. Let's talk about resonance now. Resonance is a completely different thing from dipole moment. Of course, it's not related in any way. Resonance is something that we see in molecules. It's a property of some molecules, not all. Some of them will show more than one structure, okay? And the thing is that not all of those structures can be isolated. They're only on paper, okay? So you can write them out on paper, but the only structure that you see is what we call the hybrid structure, okay, of the compound. And in between, you draw a whole bunch of contributing structures. So a compound can have up to 4 or 5 contributing structures, but only one is going to be the hybrid structure. Okay, so you take all of the 4 or 5 and then you combine them into one. Typically, the more contributing structures there are, the more stable the molecule is. Most of the resonance structures are drawn by using curved arrows, which shows movement of electrons, whether it's a 1 electron or 2 electrons. That is determined by which molecule we are talking about. So in any case, where do you see resonance? You will see resonance in structures where electrons can move around. So for example, compounds that have lone pair of electrons, compounds that have ions, like anions and cations, or where compounds have double and triple bonds. So wherever there is a place of excess electrons, then it can move, or where there is a vacancy of electrons, like in cation, that's where the electrons will move. And so molecules can have resonance structures. Now, the contributing structures that we talk about in resonance, not all contributing structures are equally contributing. Some structures may be more stable, some may be less stable. So just because we are writing a structure out for a compound doesn't mean that it's going. So what are the rules of writing resonance structures? First of all, most important thing you have to remember is that these structures exist only on paper. So we write them out, but we know that we cannot isolate them. Okay, so we will never really know whether this is truly a structure or not, but we could take a pretty good guess, okay, that this is going to be because of how we can write these things out. The resonance forms are indicated by use of double-headed arrows, which is this arrow right here. That's how we show transfer of electrons. Only electrons are allowed to move between resonance structures, okay, which means that you cannot move an atom, all right? Only electrons can move around. You can move them to 1 bond, 2 bond, 3 bonds, the electrons, no problem at all, but you cannot move the atoms. As soon as you move an atom, you actually change the structure of the compound, so you cannot move an atom, all right? So only move electrons, which again is a negative charge or a double bond, whatever it is, okay? And so if you look at this example over here, the third one here, this structure, okay, this is not going to be a resonance structure, because if you look at this one, the third one, and compare it to the second one atom has moved from CH3 over here to a CH2 over here. Okay, this was a CH3, this is a CH, but in this structure, the hydrogen atom has moved from the first carbon to the second one, and that is not the rule for writing resonance structure. So this is not a contributing structure, this is not even a resonance structure, this is some other thing. Okay, and so that's not a resonance structure. All of the structures must be proper Lewis structures, which means that they still have to obey all the laws that we have learned about writing Lewis structures, of the octet rule, the duet rule, all of those kind of things. So for example, this carbon over here is totally not a happy carbon. 5 bonds on carbon is not a happy carbon, so this is not a good Lewis structure, okay, okay, going on. The energy of the actual molecule then is going to be lower than the energy of all single contributing forms, which means that by the time you get to the hybrid, it should be very low in energy, or it should be nice and stable in energy. So it's not really a rule, it's one of the outcomes, okay, of drawing resonance structures. If you have two equal resonance structures, then they will make equal contribution, okay? So we will talk a little bit about what makes an unequal one, but otherwise, most times if they're equal resonance structures, they will contribute equally. So for example, right here in the benzene, if you look at the structure here, this has a double bond, single bond, double bond, single bond, double bond, single bond, alternate double bond and single bond. And you can move the double bonds to a different location, but it essentially looks the same as this one. So which means that both of them are contributing equally, all right, to the final resonance structure. So this is the final representation of the hybrid structure for benzene. The unequal resonance structures contribute based on their relative stabilities, okay, which means that if a structure is more stable, it contributes more. If it is less stable, it will contribute less. So what is a more stable structure? Okay, so let's look at the stability over here. The stability depends on, first of all, the total number of covalent bonds. The more covalent bonds there are, the more stable a contributing structure is. What does it mean by covalent bonds? It means it is the electrons are bonded rather than in form of a charge, like a positive or a negative. Okay, so this structure here is going to be more stable than structure number 7 or 8. Even though 7 and 8 are equally fine, they're okay resonance structures, they are writable, they're not wrong, but they're not stable. Okay, and so they don't contribute much. And again, why are they not stable? It's because of this charge distribution that we have here. In the case of 6, all the electrons are bonded. So this is a lot more stable structure for this compound. And then here, the ones that are not contributing very well for resonance structure is one in which case there is a charge, okay? And which atom can take a charge better is an important thing. So for example, more electronegative elements will take the negative charge better, more electropositive will take the positive charge better. And in this case over here, carbon is not a very happy camper, but here in this case, in this structure number 10, carbon is happier. Okay, and so it's really important that all atoms be more stable. Okay, oxygen is still stable over here and it is stable here also, but carbon was not stable in 9, but carbon is more stable in 10 because of the octet. Okay. And then in these cases where separation of charge happens, which we saw in the previous slide also, whenever there is a charge separation, those structures are not very good structures, okay, again because of the number of bonds present. Okay, in this case 11 is going to be a lot more contributing structure than structure number 12. And again, this is what I was saying to you before, is that negative charges should be more on the electronegative elements. So for example, an oxygen can carry the negative charge a lot better than carbon can. So that structure will be preferred over. Okay, and so the positive should be on the less electronegative atom, which means carbon can carry the positive better, not the negative. Okay, and so that's how you decide which structure is going to contribute more or less to. Let's look at an example over here for nitrate ion. The nitrate ion has nitrogen in the middle and has 3 oxygens. Nitrate ion is NO3 minus. Okay, and if you look at the total charge here, there is 1 positive on nitrogen and 2 negative oxygens, so the total charge is -1. You can calculate the formal charges on each of these. That's how we came up with these charges, and that's why you need to learn the formal charges as well, so you know where to put the positive and the negatives. But anyhow, writing the resonance structure for this. So once you start with one structure, now you can start moving the electrons around. How do you move them? You look at where you have the electrons. So here oxygen has the electrons because oxygen is negatively charged. You can start from this oxygen or this one. It doesn't really matter because these 2 oxygens are equal. This oxygen is different because it has a double bond. These 2 oxygens are different because they have an extra electron. So you can start the resonance structure from this oxygen or this one. It doesn't matter. So we started with this one here. And the electron pair is coming down to the bond. But because it's coming down to the bond, nitrogen is going to have more electrons that it can hold, and therefore the electrons from nitrogen-oxygen double bond are going to move to oxygen over here. Now remember, a bond is a pair of electrons, and then here also we are moving a pair of electrons. So the final structure then is a pair of electrons here, which is resulting in a bond, and those pair of electrons actually move right here to oxygen. Oxygen has 2 lone pair of electrons here and 3 lone pair of electrons here, which results in an excess of 1 electron. Now you can take electrons from this oxygen, move them to this bond over here, and then now this double bond will go right back there. And so you get a double bond here and a negative charge back there again. So at any given time, there is one double bonded oxygen in any of these structures and two single bonded oxygen, okay, in these structures. When you look at these structures, you might think, hey, they all look alike, okay, and that is true. In this case, they do all look alike, okay. In case of the nitrate ion, in some of the small molecules, the structures look alike, which means that all of those structures are equally contributing because they're all alike, okay. And so it doesn't matter. That's not our problem. If we can move the electrons around, then it's fine. And if all structures are all contributing, that is fine also, all right. So don't worry about that. They all look alike. So long the electrons are moving, okay, that's what makes a new resonance structure. This final structure over here shows the hybrid, okay, of the nitrate ion. This is a 2/3 negative charge. This is a 2/3 negative charge, 2/3 negative charge. And look at this dotted line, okay. All of this means, first of all, that the oxygen does not have a complete negative. And the second thing is that the bond between oxygen and nitrogen is not quite really a double bond. And that is because these electrons here during resonance are moving so fast that the bond doesn't really know whether it is a single bond or a double bond. So the switch is so fast that the bond is kind of an intermediate between a single and a double bond, which means that the bond is an average of the bond length for nitrogen and oxygen, okay, which means that it is an average of the single bond and a double bond in the final hybrid structure. The two things that are important for resonance and how we know that resonance actually exists is one of this fact, okay, about the bond length. The bond length for nitrate ion is between a single bond and a double bond. That tells us that there is something else going on, because if it was just simply a nitrate ion with two single bonds and a double bond, then we will have two different bond lengths for this molecule, for this ion, but we don't have that. We have a single bond length for all of these bonds, and that indicates that there is something else going on, which is why we can come up with something like resonance in which electrons are moving. Otherwise, there is no resonance, okay, which means in that case we should see the two single bonds and double bonds, but because we are not seeing that, we know something else is going on. And it has shown that all three bonds are equal in length, which means that the electrons are equally distributed. That's number one. Number two, the thing is that the bond energy of these bonds are alike. Again, if you have a single bond and a double bond, you'll have different bond energy. A double bond is stronger than a single bond, and therefore it will be harder to break. But it's seen that the nitrate ion, they have all the same bond energy, which means that there is something else going on, which is called resonance. Okay, and so we have the average of the double bonds and single bond that's going on for bond length, and then of course the bond energy, which kind of verifies for on. Here are some more examples for resonance, and again, note the arrows, okay, and note the arrows as in they're all double-headed arrows. They are curved arrows. The curved arrows indicate transfer of electrons, and we will talk about this in organic chemistry and discuss all the different kind of arrows that we have. And again, you can see the movement over here from a double bond to the oxygen, and then the transfer of these lone pair of electrons to this bond over here. So the final structure you end up getting is a double bond between this, because the carbon and oxygen, because that's where the electrons moved, and the electrons from here had moved to this oxygen, so it has now excess of electrons. This curved arrow here again shows movement of electrons, and I want to point out that this electron here, this arrow over here is a double-headed arrow, and this is what is shown for resonance. Please remember, this is not the same arrow as equilibrium, okay? So you cannot draw the same arrow. This is the arrow for resonance, and when we draw this arrow, it indicates to us that these are resonance structures. In case of equilibrium, you really have an equilibrium where you can push things forward and backward, okay, as in a reaction, but this is not something like that, okay? All right, the carbonate ion will be the same as the nitrate ion because you can see the movement of electrons all over the place. So the hybrid will be where you have a carbon with a partial double bond and single bond between the carbon and oxygen, okay? And then the negative charge is distributed all over the 3 atoms, okay, of oxygen. All right, and here is acetone, and if we add base to it, you create a charge distribution. That's not the important part. The important part is that if there is excess electrons on carbon, now we can move those electrons to here, and the electrons from this double bond can move on to the oxygen. Why do they move to oxygen and not to not these electrons to carbon? Well, first of all, oxygen is more electronegative. That's why electrons will move to oxygen. And the second thing is that this is where the double bond is. So that's where the electrons are going to move from. Okay, so you cannot move the electrons from here to say this carbon. Okay, so move them to the more electronegative element, move them from double bonds, move them from negative charges, or as it was here also in the negative charge, that's how you would move it. Okay, so this is for acetone, and again, once you move these electrons here between carbon-carbon, you get a double bond here. These electrons had moved to the oxygen, so you get a negative charge over here. The hybrid for this structure would be that you have the single bond and then you have a dotted line here between carbon and oxygen, and then this carbon and this carbon. That would be the hybrid. So one last thing to talk about in this one, and that is the different kind of arrows that we have in organic chemistry. Organic chemists are very, very picky about their arrows, okay? So I need to make sure that you know what all these arrows are and draw them correctly, okay? All right, so the first one, which you have seen a lot in Gen Chem, is the synthesis arrow, which is a yield arrow, okay? Straight shot, here it goes, okay? Reactants here, products here. The second one is the equilibrium that you've seen in Gen Chem 2. And equilibrium is when the reactants and the products are in equilibrium with each other, and they're going back and forth all the time. This arrow is the one that we just learned new, and this is called the resonance arrow. And this is double-headed arrow, as we say. And remember, in these cases, the structures that are on the left and on the right are not in equilibrium. They are independent structures, okay? And the only thing that is moving in there are the electrons. This arrow, which is a double arrow pointing to the right, this is what we call a retrosynthesis arrow, which in organic chemistry is a backward arrow, okay? So instead of a synthesis, this is retrosynthesis. This is going back, and this is because when we have large synthesis to do, we start from a large molecule and then we work our way backward, okay? And that is the retrosynthesis. So we have large molecules and we have multi-step synthesis. So it's much easier to start from the molecule rather than trying to figure out how to start from a small molecule. So it's easier to work your way backward. And so that's the retro arrow for us. This one you just learned also, which is the transfer of 2 electrons, which is a curved arrow and double-headed. Okay, that's what we used in resonance. We will also use this in reaction mechanisms. We will use this all the time, okay, in organic chemistry. The last arrow is also a transfer of electron, but this is a transfer of only 1 electron. So if you notice this, this is what we call a half-headed arrow. So the full-headed arrow shows transfer of 2 electrons. The half-headed one shows the transfer of only 1 electron. So these are all the different arrows that we use in organic chemistry. Please know them well, as we will be using them. Okay, see you in the next chapter.